From Tabask, primordial darkness of the early universe, the very first stars were born. For billions of years, these celestial giants lived and died in spectacular fashion, forging the elements that would one day become planets, moons, and life itself. This is the story of how one ordinary star, nestled in a quiet corner of the cosmos, came to shape an extraordinary world. Our cosmic home is the Milky Way galaxy, a magnificent spiral of hundreds of billions of stars, vast clouds of gas and shimmering dust stretching over 100,000 light-years across. Somewhere within one of its winding spiral arms, a region we call the Orion Arm, a new chapter in cosmic history began 4.6 billion years ago. It was here that a new star started to form. That star would become our Sun. Unlike the colossal, short-lived stars that blaze brightly and die violently in supernova explosions, the Sun is a medium-sized, long-lived star. It is remarkably stable, a quality that would prove essential for nurturing life over billions of years. The Sun's journey began within a giant, cold, and dark cloud of gas and dust known as a molecular cloud. These cosmic nurseries are composed mainly of hydrogen and helium, the lightest and most abundant elements in the universe, along with trace amounts of heavier elements forged in the hearts of earlier generations of stars. At some point, a trigger event occurred. Perhaps it was the shockwave from a nearby exploding star, a supernova, that disturbed this placid cloud. This disturbance caused a dense pocket within the cloud to begin collapsing under its own gravity. As this region of the cloud contracted, it started to spin, much like a figure skater pulling in their arms to spin faster. As the collapse continued, gravity relentlessly pulled most of the material toward the center, forming an increasingly dense and hot core. The rest of the matter flattened out into a vast, rotating disk surrounding this central proton. This elegant and powerful explanation for the birth of our solar system is known as the solar nebula hypothesis. It beautifully accounts for the formation of not only the Sun at the center, but also the planets, asteroids, and comets that orbit it in a relatively flat plane. For hundreds of thousands of years, material continued to fall inward, accreting onto the central core. The pressure and temperature at the heart of this protostar rose dramatically, reaching unimaginable levels. When the core temperature soared to approximately 15 million degrees Celsius, a critical threshold was finally crossed. The conditions were now perfect for the most powerful process in the universe to begin: nuclear fusion. In that fiery crucible, hydrogen atoms, the simplest of all elements, began to fuse together to form helium. This reaction released a colossal amount of energy, and in that brilliant flash, the Sun was born. This newly generated energy created a powerful outward pressure that pushed against the immense inward pull of gravity. This created a state of perfect balance, known as hydrostatic equilibrium. It is this delicate, self-regulating equilibrium that allows the Sun to shine with incredible stability, day after day, year after year, for billions of years. It prevents the Sun from either collapsing under its own weight or exploding from its own energy. Every single second, deep within the Sun's core, a staggering 600 million tons of hydrogen are converted into helium. In this incredible alchemical process, approximately 4 million tons of mass don't just disappear. They are transformed into pure energy. This energy, in the form of high-energy photons, begins a long and tortuous journey outward from the core. It can take hundreds of thousands of years for a single photon to zigzag its way through the dense solar interior to reach the surface. Once it finally breaks free, it radiates out into space as heat and light, the very sunlight that sustains us. The fundamental principle governing this conversion of mass into energy was described by Albert Einstein in his famous equation: energy equals mass times the speed of light squared. On a cosmic scale, the Sun's size, its temperature, and its stability are not particularly extraordinary. There are countless stars just like it throughout the Milky Way and beyond. Yet, for us, these characteristics are precisely what make life on Earth possible. If the Sun were much larger, its immense gravity would cause it to burn through its fuel far too quickly, long before complex life could have a chance to evolve. If it were too small, it would provide too little heat and energy, leaving our world a frozen, lifeless rock. The sun will continue to shine steadily in its current state for another 5 billion years, a reliable powerhouse quietly fueling the delicate, interconnected systems of our planet. In its steady, life-giving glow, the story of Earth would soon begin. From a cloud of swirling dust and fire, a planet is about to emerge, one that will cool, change, and eventually awaken.